Hey everyone, welcome back to the Foundry by Forge College. I am so pumped to have you here today. So in our last explainer, we wrapped up choosing the right network for your deployment, which was all about, finding the perfect home for our decentralized apps. But today we are zooming way in. We are popping the hood and looking straight at the engineering blueprint of advanced mapping and structs usage. Specifically, we're going to master state mutability and storage patterns. It's a really key part of our applied Solidity development track, nestled right inside the Ether and Advanced State Management module. So, let's get right into it.
Okay, let's dive into this mechanical review. Quick roadmap for today. We'll start with the blueprint, then look at storage versus memory. After that, we'll tackle the memory trap, accidental overwrites, designing clear APIs, and finally, wrap up with some checkpoints.
Section 1. The blueprint. Visualizing contracts. To really wrap our heads around state mutability, we have to look at a smart contract not just as lines of code, but as a complex machine. Our starting point here is a nested mapping. Just think of it like a giant master filing cabinet. A user's address points to a specific drawer, and inside that drawer is a set of folders. Each folder holds a custom data structure, a struct, that represents an item in their inventory. Now we've got this inventory store contract that does exactly this. Works wonderfully in theory, but in practice? Well, actually, scratch that. It is secretly riddled with fragile state bugs just waiting to break our application. Let's find out why.
Moving along to Section 2, storage versus memory, where your data lives.
Now, what's really interesting is that this entire concept highlights the absolute biggest engineering flaw developers make in Solidity, which is confusing exactly where your data actually lives. Let me ask you this. Have you ever spent hours, literally hours, carefully editing a document, pouring in brilliant, life-changing ideas, only to realize you were writing on a read-only photocopy, and the original file is just sitting there completely unchanged? Oh man, it's the worst. Well, that is exactly what happens in your smart contracts when you confuse storage and memory. Storage is the master ledger. When you write to storage, you are permanently modifying the contract state on the blockchain, period. Memory, on the other hand, well, that's your photocopy. It's an ephemeral scratchpad, perfect for read-only snapshots, but it completely vanishes into thin air the second the function finishes running.
Which brings us to Section 3, the memory trap, losing data updates.
So, let's look at how this photocopy mix-up creates our first major bug. We call this the memory trap. Imagine you write a function called increment quantity that's meant to add items to a user's inventory. You declare a variable as item memory to fetch the struct. You update the quantity. The code compiles, everything looks fantastic, but under the hood, no way. You just took a photocopy of the struct, updated the quantity on the photocopy, and immediately threw that photocopy directly into the trash. The master ledger was never touched, and your user's actual inventory remains totally unchanged. Not great, right?
Luckily, fixing the memory trap is super straightforward. Just a quick 3-step process. Step 1, locate that pesky memory keyword in your function. Step 2, swap it out and change memory to storage. Step 3, mutate the field directly. By using the storage keyword, you aren't making a photocopy anymore. You are creating a direct alias, a pointer straight to the exact storage slot inside your nested mapping. So when you change the quantity now, that change goes straight to the blockchain and persists permanently. Boom, fixed.
Let's move to Section 4, accidental overwrites, wiping metadata.
Now, let's see how this builds into an even more destructive error. The accidental overwrite happens when you basically use a sledgehammer to fix a watch. Let's say we have a reset item function, and all we want to do is drop an item's quantity back down to 0. Easy, right? Well, a really common mistake is to create a completely new blank struct with a 0 quantity, and then assign that entirely new struct back into the mapping. The problem? You just zeroed out everything else. You unintentionally erased perfectly good metadata, like the item's name, its historical ID, the whole shebang. You wiped the entire folder clean just to change one single number. And this brilliantly illustrates why we need to be extremely precise. The fix here requires 2 simple steps. First, pull the storage reference just like we did before. Second, assign only the specific field you want to change. So, for example, it.quantity equals 0. This is the surgical engineering fix. It leaves all the other metadata completely intact and perfectly preserves the rest of the struct as your blueprint evolves over time.
All right, on to Section 5, designing clear APIs, robust architecture. So now that we've patched up our bugs, let's talk about structural best practices. These are the golden rules for a robust architecture. And naturally, these are the exact same robust design principles we teach across Forge College's learning programs. Rule number 1,
Split your read-only getters from your explicit mutators. If a caller just wants to see their item, give them a memory snapshot. If they want to actually change it, use a dedicated mutator function that accesses storage. Number 2, never, ever return mutable storage pointers unsafely to external callers. Just don't do it. And third, when you create a brand new item, safely initialize it directly in storage. This avoids unnecessary copying and ensures it immediately persists to the master ledger. Finally, Section 6, Checkpoints. Time for a diagnostics check.
So, the crucial point is we need to prove that our mechanical fixes actually hold up under pressure, right? Let's look at our debug report. When we run our tests, the before and after behavior should match these exact expected states. If we create and read an item, the ID, quantity, and name absolutely must all be present. When we increment the quantity, that quantity must increase persistently, so no more memory traps. And when we run our reset item function, only the quantity zeroes out while the name stays completely intact. You've got to rigidly review these state tests to guarantee no data is ever lost. It is absolutely crucial.
Okay, so your state mutability is rock solid and your storage is totally secure. But here is the next big question for you. How fast can you retrieve it? Now that we have a bulletproof nested mapping, we need to optimize it. And that brings us right into our next lesson in the track, Efficient State Retrieval Patterns. Thank you all so much for joining me on this deep dive. Be sure to visit forge.college to master more Web3 blueprints, dive into our applied programs, and take your smart contract engineering to the next level. I'll catch you in the next explainer.